Okay, so in this lecture, we will talk about non-convex optimization applications. Right? If you recall, the organization of this class is we will talk about problem with increasing complexity. Right? We'll start with unconstrained optimization problem, then we talk about linear programs with linear constraint. And then we talk about nonlinear programming with nonlinear constraint, but mainly focus on convex problem. Right? And then we talk about like branch and bound cutting planes for solving mixed integer linear programming problem. And now in this lecture, we will start talking about applications and algorithm for solving non-convex optimization problems, non-convex, nonlinear. Okay, so let's first give a formulation of the problem we will cover. What is non-convex continuous optimization problems? Here, let's assume all the variables are continuous. And then you have some objective function and some equality constraints and inequality constraints. Okay, so then the feasible region denoted by all the constraints is a convex set when any of these function h of x is non-convex or this equality constraint is nonlinear. Right? Remember, when we talk about convex optimization problems, in order for the feasible region to be convex, we assume all the h of x are a convex function and all the equality constraints are represented by a linear function. Now, if any of those, either any of the hi of x are non-convex or any of the inequality constraint is nonlinear, then x can represent a non-convex set. Okay. So that's what we will talk about for the next few lectures. All the methods we talk about are methods that solve this non-convex optimization problem to global optimality. There are also other methods that can solve non-convex optimization problem to local optimality. That's not the focus of the, this class, right? So there are methods that can give you one of the KKT points of a continuous optimization problem, but we are not going to talk about that. We will focus on methods that can guarantee global optimal solution to this problem. Okay. So why I said non-convex optimization is more complicated than mixed integer linear programming. You can easily show that mixed integer linear programming is a subset of what is called QCQP, means quadratically constrained quadratic program. Okay. The reason is for any of the binary variables, that is 0, 1, it is equivalent to state the y have to satisfy the following constraint: y times y minus y equal to 0, because the only roots to this equation are 1 and minus 1, right? So if you have this constraint, you have a quadratic constraint, right? Because this is like you have a y times y, right? Y squared equals to y, right? So that's a quadratic constraint, not a linear constraint. But when y satisfies this quadratic constraint, y can only be 0, 1, right? So if you can represent this constraint, then you don't need the binary constraint anymore, right? So therefore, quadratic constraint is more general than mixed integer linear programming constraint. Okay, that's what this claim is, right? So that's why I said this form is more complicated or more general than MILP. Okay. Of course, you can add another level of complexity by saying not only we have those nonlinear non-convex constraints, but I also want to add some binary variables, right? So I add binary variables y belongs to 0, 1, and then I have general nonlinear non-convex constraints related to x and y. This is called a mixed integer nonlinear programming problem. In particular, in this mixed integer nonlinear program, if functions f and g are convex, h is linear, we call it convex mixed integer nonlinear programs. So this name can be quite confusing, but it is sort of a convention in this area. of course, when you have a mixed integer nonlinear program, itself must be non-convex because you have binary variables, right? So when we say a convex MNLP means if you relax a binary variable, the rest of the problem is convex. Then we say it is a convex MNLP, right? Because if f is a convex function, g is convex, h is linear, then if you relax a binary variable, this is a convex nonlinear program. Right? So by convention, we say it is a convex MNLP. Okay. The continuous relaxation is linear. We shouldn't see that. So should say it's a convex. Otherwise, it is called a non-convex mixed integer nonlinear program. Okay. Okay, so we will first talk a few applications about non-convex optimization problem before we introduce the algorithm to solve those problems. Most of these problems can be, I talk about in this lecture, can be handled by Groovy because they are quadratically constrained quadratic programs. But now with a new version of Groovy, it can actually handle general mixed integer nonlinear programming problem. Therefore, if you want to solve this problem, you can still model them in Pyomo, but make sure you update your Groovy version to the latest version in order to solve all the problems I talk about in this lecture. Okay. Now, let's start with the so-called packing problem. The idea is you want to pack some objects into a container, or you want to cut a material into different types of shapes. It has very wide applications. For example, in manufacturing, right? In industry like garment, metalworking, woodworking, right? The idea is you want to cut some materials into predefined shapes, right? For example, if you are making clothes of different sizes, right? You have L, M, X, XL, small, and so forth, right? You have a huge piece of cloth, and you want to cut this cloth into different types of sizes, right? How do you save the material when you cut this piece of material, right? And then it also has applications in logistics and shipping, right? Imagine you have some cargo ships, and you have a big container, right? The container is not, let's say, fully packed, right? But you want to pack items of different shapes into the container such that you can save the number of containers when you are dealing with transportation or shipping. And it also has application in computer science and data storage, right? So how do you best allocate memory or in cloud computing, right, to maximum efficiency? Okay, so I'm not going to talk about packing problems in general, but we will talk about some very simple packing problems. Okay, so now probably the simplest packing problem is packing circles in a circle. The problem statement is the following. We are given a number of very small circles, and then we need to find the smallest circle that can pack all the small circles. Okay, so let's say you have these small circles represented by A, B, C. They are different types of small circles, and then you need to find a smallest circle that can pack all the small circles. You want to minimize basically the radius of this circle that can pack all the small circles you want to pack. Okay. Now, of course, you are given the radiuses of all the small circles. Right? They are denoted by Ri. And the variables we define is suppose the centers of the big circle is the origin, and then the coordinates of the small circles are xi and yi. Right? So once you assume the center is the origin, and then once you give the center of the small circles, then basically that fully describes where the smaller circle are located. Right? To decide where the small circle is, you only need the coordinate and the radius of the small circle. Okay. So how would we formulate this problem? Without going to the math, let's think a little bit about what type of constraints we need to have. If you want to pack up all these small circles into a big circle, right? And you want to minimize the size of this big circle. Yeah, you can describe the constraints in words. Yes.
Well, we know that the area of the large circle is at least as big as the area of all the circles combined.
Yeah, that for sure, right? Otherwise, the smaller circles will have to overlap, right? So therefore, based on your argument, you're actually talking about so-called a non-overlapping constraint, right? The smaller circle cannot overlap with each other, right? What other constraints do we need to have? Right. Yeah.
Circles must be within a bigger one.
Yeah.
They cannot be outside.
Yeah, exactly right. So they cannot go outside the big circle, right? First of all, the small circles cannot overlap with each other. Then the second constraint is like the small circles cannot go exceeding the boundary of the big circle, right? So when you formulate an optimization model, first of all, describe the variables and constraint in words, right? And then converting your words into math. Right? That's it, okay? So now let's formulate this problem, right? Okay. Assuming R0 is the radius of the big circle, right? Ri is the radius of circle I. The first constraint specify each circle is within the big circle. Okay, so that means consider of course the origin is here, and then the coordinate of a small circle is xi, yi, right? And then the radius of the small circle is ri, right? So then, if you connect this, the coordinate plus the direction of the radius should be less than or equal to the radius of the big circle, right? So basically, the distance, the Euclidean distance from the center of the small circle to the origin is the square root of xi squared plus yi squared, right? And then everything of the small circle should be within the big circle, right? So if this distance plus ri is within the within the big circle, the whole thing is within the big circle, right? Because this direction is the longest distance you can get away from the origin. Okay, so that's what this constraint is. The distance from the origin plus the radius has to be less than or equal to the radius of the big circle. And the second constraint is so-called non-overlapping constraint. Right? If you calculate, let's say here is one small circle, let's say x1, y1, and this is another circle x2, y2, right? And then this notation is the distance between x1, y1 and x2, x2, right? This is the Euclidean distance of the centers. And distance between the two centers must be greater than or equal to the addition of the radius of the two circles, right? So with this constraint, they will not overlap, right? Their distance is far enough. Okay. Now, is this problem convex? It is not, right? Because you have some square root terms and so forth. but it can be represented as a non-convex QCQP. The reason we want to represent this as a QCQP is because there are some special tricks for solving QCQPs. We will talk about that in the next lecture. So you could put a square on both sides of the inequality, then you can convert, for example, this constraint to a QCQP. Right? You get rid of the square root, but then you have some square term here. Okay. So this is circle packing in a circle. Now the next problem we will cover is so-called circle packing in a rectangle. Right? You can think about you have some circles, you want to pack it into a container. Usually the container is a rectangle. Right? But in the previous case, a container is also a circle. Now similarly, we will have non-overlapping constraint, and also the circle cannot exceed the boundary of the rectangle. Right? But the rectangle is slightly more complicated. Right? So we need to consider the x and y coordinate respectively. So let's assume A and B are the width and the height of the container. So in other words, let's assume the origin of the container is 0, 0, and then you have a container of this shape. A is the, well, I'm not drawing it very well. So let's say this is origin, and then this length is A over 2. And then this length is B over 2. Okay. Now you want to pack circles into the rectangle, right? In order for the circle to stay within the rectangle, we need to consider the x-axis and the y-axis separately, right? Because the circle is symmetric, and then the rectangle is also symmetric. It's not that hard. So let's assume you have a circle here. Whose coordinate is xi. Okay, so let's say the coordinate is xi, yi. Right? So what will be the constraint we need to add for the circle to stay within the rectangle? Right, the x coordinate is xi, and then y coordinate is yi. Let's first consider the x coordinate. So it is easy to see that in order for the circle to stay within the rectangle, we only need to make sure the 4 points, 4 orthogonal points, let's say this point, this, and this. Right? As long as these 4 points stay within the rectangle, the circle stays within the rectangle, right? Because of the symmetry and then the way the shape works. Okay, so how do we make sure these 4 points stay within the rectangle? Right? So let's say this rightmost point. Right? The x coordinate is xi, right? So then change a different color. So this coordinate would be xi plus ri, right? That's the x coordinate of this point here, right? And the x coordinate of this particular point is xi minus ri, right? So as long as these right and left points stay within the rectangle, then at least we do not violate the width constraint, right? The height constraint still may be violated. So how do we specify these 2 points are within the rectangle? Yes?
Just the xi minus ri is greater than negative a halves.
Yeah.
Xi plus ri is less than positive a halves.
Right, exactly, right. So we only need xi minus ri to be greater than or equal to negative a over 2, and then xi plus ri to be less than or equal to a over 2, right? Then these 2 points will stay within the rectangle. And similarly, you can do it for the y-axis, right? I will not dwell on that. So yeah, so basically you got these 2 constraints, and then for the y-axis, you got these 2 constraints. Okay. Now the other thing is a non-overlapping constraint I did before, right? You can calculate the Euclidean distance of any 2 circles. That's just the square root of the difference between x and y coordinates. And the distance has to be greater than or equal to ri plus rj, right? Same thing as the previous case. And then you may need to constrain a and b, right? For example, you cannot make it too high or make it too wide. Then you have some bounds on a and b. And the objective is to minimize the total area of the container, a times b. Okay, any questions? Sure. I will switch gears and talk about this problem called continuous facility location. You may recall the problem called incapacitated facility location problem. That is one of the applications of mixed integer linear programming. Right? In that problem, the depot are pre-selected. Right? So the idea is you need to build some depot to serve all the customers. Right? And then in a region, there are multiple depots you may want to build. And then in that problem, the decisions are binary, right? Whether you are building a depot at a particular location or not. And the locations of all the depots are pre-selected in incapacitated facility location. So in this continuous facility location problem, the idea is I give you a wide range of area. You can decide arbitrarily where you want to build your depot. Right? So let's say you have a given area, and then let's say these are your customers. Now you need to build some depot to satisfy the demand of your customer. In the incapacitated facility location problem, the location of the depot are pre-selected. So let's say these are the depots. And then you can select any of these 3 depots. I'll give you the location of these depots. There is some binary variable associated with whether building the depot or not. In the continuous facility location problem, I do not specify the location of the depot. You can build depots in any coordinates in this area. So that's why we call it continuous facility location, because the coordinates are continuous variables. Okay. Yeah. So how do we model this problem? Again, the problem statement is consider a set n of potential depots and a set m of clients with associated fixed cost fj for depots and unit variable transportation costs from j to client I. The location can be selected anywhere on a 2D plane. The known parameters are the coordinates of the clients or your customers. You do know the location of your customers. And the variables include zj equals to 1 if depot j is used, zj equals to 0 otherwise, right? So as you can imagine, there are some symmetry between depots, right? You don't need to build all the depots here. And wij represent the fraction of client's i's demand satisfied from depot j, right? It is an incapacitated problem, right? If you are a given client, you can satisfy your demand by any of the depots. And then wij represents the fraction. And xj, yj represents the coordinate of the j's depot. Right? Again, xj and yj are continuous variable. You can select the location of your depot anywhere on the 2D plane. Okay. Is this problem statement clear? Okay. Now, the objective include the fixed cost, right? So this part here is a fixed cost. Zj means whether you are building a depot or not. Once you build a depot, there is a fixed cost, okay? And there is also variable cost, right? So the Dij represent the distance between the depot to the customer. And then Cij is the cost, like the unit cost. Wij is the fraction of the demand satisfied by a given depot. Right? The first constraint is demand satisfaction constraint. Right? Each customer's demand has to be fully satisfied by the sum over all the depots. Right? So that's why you have this sum over sum over j from 1 to n equals to 1. And then this constraint is a logic constraint. It will force the Wij to 0 if the depot is not built, right? Just like in the facility location problem. And Dij is the distance calculation, right? If you want to ship some product from one location to another, the transportation cost will be proportional to the distance. Okay, so this is the distance of between two locations. And Wij is greater than or equal to 0, Zj is a 0, 1 variable. Okay. So the thing here is after we change the coordinates of the facility to be continuous variable, this becomes a non-convex problem, right? Because you have this distance calculation here, and then you want to minimize the distance. Okay. Yeah, actually you can square it, and then no, you cannot really do that because you need a square root here. Okay, so that's a continuous facility location problem. Then we also have a related problem called k-means clustering. In the MILP application, we said the facility location problem is similar to something called k-Madois clustering problem. Right? In k-Madois clustering, the idea is the center you pick has to be a data point. But in k-means clustering, the center you pick does not have to be a original data point. Okay, so what is k-means clustering? If you have studied machine learning before, you may heard about this. Right? It is one of the popular clustering algorithm. So the high-level idea is the following. You have a bunch of data points, and then you want to divide the data points into, let's say, k equals to 3 here, 3 clusters, right? Then you want to find the points to be close to each other, right? So let's say you have divided the points into 3 different clusters, and the points within each cluster are close to each other, okay? So mathematically speaking, the idea is you want to partition the data points into 3 subsets such that the within cluster variance is minimized. So what is within cluster variance? That means you want to minimize the summation of the variance of the 3 clusters, right? So when you calculate the variance of this cluster, you will only consider the points in this cluster, right? So consider the variance of this cluster plus the variance of points in this cluster plus the variance of points in the 3rd cluster, right? You want to partition in a way such that the sum of the variance is minimized, okay? Or you can think about you want to minimize the squared Euclidean distance between the data points in the cluster and the centroid of their assigned cluster, right? Because if you want to minimize the variance, you should pick the point as the mean of all the cluster, right? So that's why it's called k-means, because the variance will be minimized if you compare it with the mean of all the data points in this cluster. So in k-Madois clustering, the difference is that the center point you pick has to be a data point, right? So if you take the mean of all the data in this cluster, they may not be a data point in the original problem, right? So you take the mean, it could be, let's say, this point. It is not a data point. But then in K-Meadows clustering, you have to pick one of the data points to calculate the distance. Let's say you pick this point, maybe. Okay. So that's sort of the difference between K-means and K-Meadows, right? It's sort of similar to the facility location problem. In the original facility location problem, you have to pick a pre-selected location of the depot, right? And just like in K-Meadows clustering, you have to pick one of the original data points. But in K-means clustering, you can pick any point in the Euclidean space, right? In continuous facility location, it's the same thing. You can pick any points in the Euclidean space. Okay, so how do we formulate this problem? You have a set of data points, sets of clusters, and then without loss of generality, we assume all the points P1 all the way to Pn have been normalized. You can always normalize the data to let each of these coordinates between 0 and 1. Okay, and then we have a binary variable to decide. It will take value 1 if point I is assigned to cluster K and 0 otherwise. And di is the distance of point I to its cluster center. And then you can use a continuous variable ckj to represent the j's coordinate of the K's cluster center. Right? So this can be changed arbitrarily. It can take any continuous values. Okay, so now, as I said, the objective is to minimize the squared Euclidean distance. So let's use di to represent the squared Euclidean distance. Okay, so how to represent di? So here I'm using a formulation with some big M type of constraint. The idea is you will only activate this constraint if a point is assigned to a cluster K. Otherwise, you just relax this constraint, right? So this yik variable means you are assigning data point I to cluster K, right? So this constraint actually is an assignment type of constraint. You will assign each point to one and only one of the K clusters. Right? That's why you sum over all the K cluster for each point I, it should be equal to 1. Okay? So if data point I is assigned to cluster K, this guy goes to 1, right? And then this big M constraint is will be canceled to 0. Then this part of the constraint is activated, saying that di should be greater than or equal to the distance calculated based on the center of the K's cluster. Right? So ckj is the j's coordinate of the K's cluster. Only if the data point I is assigned to the K's cluster will this distance calculation be activated, right? You don't need to consider the distance from all the other cluster centers. Okay. Is this part clear? Yeah, now let's talk about one of my favorite problems in chemical engineering called the pooling problem. This is a problem very widely solved in the chemical industry. Especially the petrochemical refining industry, and some people also solve it in wastewater treatment or natural gas network design. Okay, so now the idea is in a petrochemical company, as we all know, right, if you go to the gas station close to our department, you can buy gas with different compositions, right? They are like 87, 80, 89, and then the other is like 90 or 91, right? So those different gas have different hydrocarbon composition, right? And then how did they make different compositions? So the way the petrochemical company does this is through solving the so-called pooling problem. So you can imagine here, they have a bunch of upstream processes, and then they can produce hydrocarbons of different compositions, right? So these are the feeds to the pooling problem. You can think about those are the raw materials with different types of compositions. And then they will mix the feeds in the so-called pools, right? So this is like a blender. You will mix all the flows going into the blender, right? And then they will become uniform concentration. And afterwards, you will split them into different streams. And here you have different product tanks, where you can think about the product tanks as different compositions, which will make, let's say, jet fuels, diesel, or gasoline, or different compositions of gasoline, right? Okay. So the idea here is it is a tripartite network flow problem, right? Where you have some feeds, some pools, and then some product nodes, right? It is so-called tripartite graph. You have 3 different types of nodes, and then they are connected between each other, okay? Now, this may still not sound intuitive enough. Let me give you a more intuitive representation, or a bit simplification of the previous problem, right? So instead of talking about hydrocarbons, let's talk about colors, right? Red and green. So let's assume in your inputs, you have 3 different inputs. They have different concentrations of red and green, right? They are only 2 different compositions. Let's just call them red and green, right? And then you need to make some products, right? In the node 6 and 7, where you have some specifications on the concentration of red and green, right? In petrochemical company, it might be, let's say, sulfur concentration cannot be over a given threshold, right? Or some other hydrocarbon concentration has to be lower than a given threshold. Okay, so different product can have different specifications on red and green, right? Maybe for product 1, you need more red, and product 2, you need more green, right? And then you are going to mix those initial materials in the pools, right? So 4 is made by mixing 1, 2, and 3, and then you got a slightly different composition for 4, right? And later on, you could send 4 to the final tanks to make products, okay? Yeah, so this is basically the summary of the specification of the pooling problem. The raw material have some specification. You do know the concentration of the raw materials, things like sulfur, octane number, and so forth. And then the raw material gets mixed at the pool, producing different specification level. And the material gets further mixed at the output nodes, right? And then in the output nodes, you are going to make your final products. They have different concentration specifications, okay? So how do we formulate this problem? We will define a lot of notations here, but you don't need to remember all the notations. I will talk about them as we go through the formulation, okay? So there are 3 different formulations to this problem, and each formulation has its sort of pros and cons. That's why we use this to illustrate the formulation, right? There are different ways of formulating this problem. So the indices include raw materials, products, and so qualities means things like octane number or sulfur concentration, right? Or you can think about them as red or green. And then we have a list of pools. As for parameters, we have cost on the raw materials, price of the product, availability of raw materials. Maybe you can set an upper bound on the availability of raw materials. You can not exceed that availability. And then we have the quality of the raw material. You can think about this as the red or green concentration of your raw materials, right? And demand of the J's product, well, the problem is like a demand satisfaction type of problem. And PJKU is the upper bound on the case quality of the J's product, right? So this is like the quality specification, right? Maybe your sulfur concentration cannot exceed this amount. That is what this PJK represent. we also have the capacity for the pools, right? You can think about the pools as some blending tank. You cannot send more than the capacity of the blending tanks. Okay, so the P formulation is perhaps the most intuitive formulation of the blending problem, but mathematically it is not a very good formulation. Okay, so we will explain why. So here, if you look at this picture, that basically represent all the variables we will define here. Right? So this is a tripartite graph and a network flow problem. Therefore, we define these x, y, and z variables to represent the flows. Right? So x represent the flows from raw materials to the blending tanks. Right? So these are the x11 is the flow from raw material 1 to blending tank 1. Right? x21 is the raw material 2 to blending tank 1. And y represent the flows from the blending tanks to the products. Right? And there can also be flows, direct flows of raw materials to the products. Right? So Z11 means raw material 1 to product 1. Okay? And then we also need to check the quality, right? Because there are some quality specifications like sulfur concentration. Therefore, you define this variable PLK that represent the quality of pool L from pooling of raw materials, case quality, right? Because after you mix the material at the pools, then you have different quality than the raw materials, right? You are mixing raw materials at the pools, and its quality will change after mixing those raw materials. Therefore, you define a variable to keep track of the quality. Okay. So one thing to note here is not the connections of pooling problem are sparse usually. In other words, this problem is not a fully connected problem. Right? For example, here one is raw material 1 is connected to product 1, but it is not connected to product 2. Right? There is no edge from raw material 1 to product 2. Right? So this problem is not fully connected. Some of the edges are removed. That represent physically you cannot directly ship from a given tank to another tank. Okay, so that makes this problem hard because if this problem is fully connected, you don't really need the blending tanks, right? You can just send arbitrarily the raw material to the products, right? So there might be some physical reasons this is not fully connected, but that makes this problem hard. Okay. So in our notation, we just treat all these variables that do not exist as fixed at 0 in the formulation to simplify our notation. Otherwise, you have to define some new notations to specify whether the edge exists or not. Right? We just assume all the edges exist, and then for the edges that do not exist, we assume the flows are 0. Okay. Now, let's first talk about the objective. Of course, you have different types of cost, right? So you can think about it as a summation of the cost of raw materials and then the revenue by selling the product. Okay, I will not go to the details. If you check the notation back and forth, this is very obvious. Okay, so now let's go through all the constraints. The first constraint is to ensure the availability of raw material is not exceeded. So AI represent the availability of raw material I. Okay, so that means for all the, let's say this is raw material 1, all the edges that are going out of the raw material has to be within the capacity. Right? So just like in this case, these are the edges going out of the raw material 1, they have to be less than or equal to the availability of raw material 1, right? And that's basically this constraint here. Okay, the x, sum of x and z represent all the edges going out of raw material I. Okay. Of course, we also need to specify mass balance. Right? This is what chemical engineering students are most good at. Right? We have mass balance. What goes into the pool here has to go out. Right? So this is the two edges going into this blending tank, and then they have to be equal to the flows out of the blending tank. Right? Simple mass balance constraint represented using this constraint. Also, we need to limit the flow into the pools by their capacity. So SL is the capacity of the pool. Right? So this is a given pool, and then you are sending these two flows into the pool. They have to be less than or equal to the capacity of the pool. That's what this constraint represents. Okay, and then we need to make sure the sales of each product cannot exceed the demand. Right? So then, for example, this is the demand of product 1, and then these two edges are flowing into the demand tank. The sum of all the flows into the demand tank has to be less than or equal to the demand DJ itself. Right? You cannot sell on what or sell more than what your customer demands. Okay. So the last constraint is a bit more complicated. This constraint actually makes the pooling problem hard, right? But because you have some quality specification on your product. If you do not have any quality specification, this is a linear programming problem because you just have a network flow with mass balance. Right? You don't need to track the concentrations of different qualities. But because here you have this parameter pjk superscript u that represent the upper bound of a given quality for a given product, right? Like a sulfur concentration for a given product. You cannot go over this quality. Right? So how do we calculate this quality? The way you would calculate this quality is the following here. Right? So here, this part, the right-hand side, represent all the flows into a given demand tank, all the Y's and Z's going into a demand tank, right? So this is a total, so this part is a total flow, flow into a given tank, J, right? And then the left-hand side represent the sum of the quality K. Right? So Zij is the flow of raw materials, and then the quality K of raw material is represented by Cik. Right? So Cik times Zik gives you the concentration of quality K from the raw material, and then Plk is a quality you calculated for the blending tanks. Right? So therefore, the left-hand side is quality K into a product tank J, right? So this is a quality of K going into a product tank J, right? So this is a total flow of the into the product tank J, right? It has to be less than or equal to this quality specification. That's what this constraint means. So last but not least, we have the balance of quality constraint, right? So remember, PLK is a variable we defined to specify the quality for the blending tank, right? So we are doing some sort of mixing at this blending tank, right? So the X are the flows into the blending tank, right? After you do the mix, the quality of this blending tank will be equal to the quality goes into the blending tank, right? So Cik represent the flow of quality K into the blending tank, and then the sum over Y is flow out of the blending tank, right? So therefore, when you flow out, it will average out the concentration of what goes in, right? So this is simply a mass balance constraint on the quality K at the blending tank. Okay. So I go through this a little bit quickly because I want to finish on time. You can check all the constraints by yourself. Okay. Any quick questions here? Right. So essentially, you have some mass balance constraint, both on the flows and on different quantities, right? Because you need physically what you need to do is to enforce some quality specifications like sulfur concentration at the product. But in order to do that, you need some equations to calculate the sulfur concentration, right? Not only you need to have the total mass balance, but you have the mass balance for each quantity, like the mass balance on the green and red, respectively. Yes?
I don't understand why we have an upper bound rather than a lower bound
Yeah.
for quality.
Yeah, so sometimes you can write a lower bound as well.
It's just for this one.
Just for this one, I just put an upper bound. You can also do lower bound. Yeah. Yeah, good point. Okay. So that's a P formulation. It's very intuitive, right? It directly gave you the flows, directly gave you the concentration at the pool. There's another formulation called a Q formulation. So the idea is instead of using these XIL variable, right? XIL represent the flow from inputs to pools. Then we are going to replace that by a percentage variable, QIL. So QIL represent the fraction of the inputs to pool L that comes from input I. Okay, so here I have a given pool 1, right? Instead of directly representing those flows as XIL, I will replace them by saying, what is the percentage of flows coming from blending tank 1 and 2, right? So that's the same thing, right? Because the total flow into blending tank 1 is the sum of Y11 and Y12, right? Maybe let's say 40% of them come from 1, 60% comes from 2, right? Then Qn1 will be 40%, Q21 will be 60%. Right? It's just another way of stating the problem. Then you can replace all the XIL variables with these Q variables. Right? So all the QIL should sum to 1 in this case, right? Because it is a fraction type of variable. Then the idea is you will replace all the XIL in the P formulation by this Q variable. Right? Then you don't need the concentration type of variables anymore, right? Since you are keeping track of the input flow. So with that, you arrive at this Q formulation, right? Where, as you can see, the X variable are replaced by this Q times Y type of variables here. Okay, and then you make some corresponding changes and got the Q formulation. Okay. Now, there is a different formulation called the PQ formulation. So the difference between Q formulation and PQ formulation is you add another redundant constraint into this problem. Okay. The redundant constraint is a following. You have QIL times YLJ equals to YLJ. This is a very trivial constraint because you have the summation of I from 1 to I, Q equals to 1, right? So you multiply this by this YLJ variable, right? So you multiply this constraint by YLJ, then you just get this constraint. Right? So you did nothing here. So why you want to add a redundant constraint to this problem? We will talk about this in the next lecture because after you add this redundant constraint, it improves the convex relaxation of the blending problem. Okay, so again, in the next lecture, we will talk about solving the non-convex problem to global optimality relies on so-called convex relaxation. That means you have a sort of have a, so let's say this is a non-convex function here. I don't know how to find the global optimal solution. But somehow I come up with a convex function that approximate this, this non-convex function. And then you can solve this convex problem to lower bound the non-convex problem. Right? Of course, you would like this, this convex function to be as close as possible to the non-convex function. Right? So if you have the PQ formulation and come up with a convex relaxation, you can show that it is better than the P formulation in the sense that it is closer to the non-convex region. That's why we add this redundant constraint. Okay. Yeah. So that's all I want to talk about for the pooling problem. Any questions here? Now let's talk about this problem real quick, so-called molecular structure prediction. Right? So maybe you heard about protein structure prediction, which got the Nobel Prize in chemistry last year. Right? The idea is give you a sequence of amino acids. You want to find the structure of the proteins that sort of minimize the Gibbs free energy. Right? Once the structure is fully determined by the sequence. Of course, they use deep learning methods to predict the structure. But then in principle, this can also be formulated as a global optimization problem where you want to find the structure that minimizes the Gibbs free energy of this problem. Right? So how do you model molecular structure prediction? There are so-called different force fields to model molecular structure. Of course, this is a very simple force field. It may not be that accurate, right? There are terms related to bound stretching, angle bending, torsion, and like Lennard-Jones potential. Right? If you use these force fields, essentially this is a non-convex optimization problem. Right? If you can solve this to global optimality, then you can get the minimum energy structure of the problem. Of course, this problem is very, very hard to be solved to global optimality. It's very highly non-convex. So lastly, I will talk about a problem on chemical process scheduling. Well, you may not encounter this problem in your research, depending on what you do. If you do scheduling research, maybe you will encounter this application. The major reason I would like to talk about this application is to showcase a very interesting trick that can convert a seemingly non-convex optimization problem to a convex optimization model. Right? So there are some problems. If you formulate the problem in a very physically intuitive way, it is a non-convex problem. Right? It's very difficult to solve. But if you adopt some interesting tricks, you can convert that into a convex problem. Right? This is my example of that type of problem. But for most of the problem, you cannot apply this trick. But some of the problems have this very nice structure. You can apply the trick. Okay. So this problem is called multi-product plant with a single product campaign. Okay, so the idea is you have a plant that can produce different products, but then you have to produce one product after another. Right? Okay, so here you have in your plant. Let's assume you have two products, product A and product B. Right? And then you need to first produce all the product A before you go to produce product B. Okay? And then in this plant, there are different processing stages. Right? So here there is a plant of different stages. In each stage, maybe you have things like mixing reaction or separation and so forth. Right? And they have to go through all the stages. Then if you have let's assume in the first case, if you have one unit at each stage, there is nothing you can do but wait for all the orders to be produced before you move to the next stage, right? So if you have a single unit at each stage, the cycle time is limited by the so-called rate limiting step, right? You have one stage that takes longer processing time than the other stage. So therefore, your cycle time of a product is a max over the processing time over all the stages, where M is a set of stages and I is product I. Right? So for product I, the processing time is the max of the processing time over all the stages you have. Right? So if you have 1 unit at each stage. Okay. And now let's assume you can have some parallel units. Not only you have 1 unit, but then maybe you have 3 units at stage 1 and 3 at stage 2 and so forth. Okay. Then the cycle time will be determined by the max over all the stages, but then the processing time can be divided by where n is a number of parallel units in stage J, right? So let's assume you can run all the jobs in parallel, then you can cut the time by 1 over n. Okay. That's sort of the setup of this problem. Now the idea is we want to minimize the cost of a multi-product, single product campaign planned. Single multi-product SPG would be single product campaign. Yeah, that means each time you only produce 1 product before you move to a different product, while you satisfy different demand. So the set involve all the products and all the stages, and the known parameters include the processing time of a product I in stage J. Sij is some sort of size factor. Right? If you have a given volume of reactor, how much can you produce per hour, for example? And Qi is a product demand. Right? So you will need to satisfy some product demand. You can split the product into different batches here. Okay, so here's what it means. So you have some product. In total, you need to satisfy Q1 and Q2 for 2 different products. You can split this order into smaller batches, right? Maybe you split Q1 into 3 batches, and then you split Q2 into 2 batches, and then they can be produced using those plans, right? And then alpha j, beta j are the investment cost coefficients. You can think about if you invest in a vessel, then the cost is alpha times the volume raised to the power of beta j. Usually beta j is less than 1 because of economy of scale. You can think about beta is 0.6 or 0.8. And h is the time horizon. All the demands must be satisfied within the time horizon, right? So the idea is you want to design a plant, right? You don't want to spend too much investment cost such that you design so many reactors, but then you are not using that. The idea is you want to satisfy the demand. Also, all the jobs have to be done within this time horizon. Okay. Then the variables include the design variables. Vj represent the volume of unit J, and Nj represent the number of units at stage J, right? Bi is a batch size of the product I. Right? If you have a total demand of the product I, and then you can split them into different batches. TL is a cycle time of product I. Okay. Now let's talk about this problem. The objective is to minimize the total investment cost of all the vessels. Right? So this part is the investment cost of a single vessel, and then Nj is the number of vessels in a given stage. Right? So therefore, this is a total investment cost, and this is clearly a non-convex objective. Right? You are minimizing a concave function. Yes.
I'm sorry, I'm slightly confused because we're saying it's single product campaign,
Yeah.
but then we're saying that we're doing it in parallel. I thought for single
Yeah.
product campaign, you can't parallelize.
So the idea is you are splitting a given product into different batches, right? So let's say if you have 3 units, and then you split a product 1 into 3 batches, then you can process the 3 batches on the 3 units right? But you are still only producing the first product.
Oh, okay, so
Right.
you're saying that we can do a single product in parallel, but we're not going to run a batch of product 1 and a batch of product 2 at the same time?
Right, yeah. So you have to first finish product A, then you go to product B. Right,
Okay.
yeah. But then you can run, multiple batches of product A in parallel. Yeah. Okay. Yeah. Yeah, but very, very good question. Okay. Now, let's talk a bit about the constraints, right? So the objective is non-convex. Let's see how the constraint look like. We have this vessel size constraint. Remember, Sij is like a size factor, right? If you have a given vessel size, what will be the amount of product you can produce? Or in other words, if you have a given batch, you need to at least have this amount of vessel size in order to produce this product, right? I think it's the other way around. If you have, let's say, batch size of Bi, then your vessel size has to be greater than or equal to this size factor times Bi, right? This is like a capacity constraint, right? You cannot produce a batch larger than what your vessel size allows you to produce. Okay. Now we have this average cycle time constraint, right? So remember we talked about this before. You could produce different product in parallel, right? If you do not have parallel vessels, then the cycle time is determined sort of by the rate limiting step, right? The longest processing time over all the stages. But then if you can do it in parallel, you can divide it by nj. Suppose you can run all the batches in parallel on the nj machines. Okay, so that's what this constraint is about. So this constraint is nonlinear, but it is a convex constraint, right? The Tij is a parameter, nj is a variable. Right? So 1 over x is a convex function, right? If x is greater than or equal to 0. Now you also have a demand satisfaction constraint. Okay, so Qi divided by Bi, so this part is the number of batches, right? Q is the total demand, Bi is a batch size, and then the ratio is a number of batches you need to produce, and TL is a cycle time of a given product. Therefore, you need to sum over all the products. Then you have to satisfy all the demands within time horizon denoted by H. Okay, so this is so-called demand satisfied within the planning horizon, right? So now you have the ratio of two variables, right? Qi is a variable, Bi is a variable. This thing is a non-convex function, okay? Now you could try to absorb the application afterwards if you are not so familiar with things like single product campaign and so forth, right? But the main thing I want to illustrate here is very intuitive formulation give you a non-convex problem, right? So this constraint is a non-convex constraint. The objective is also a non-convex function, right? So there is a very interesting trick that can convert this problem into a convex problem. Okay, so we will talk about that. Okay, so the trick here is taking the log transformation of each variable. Okay, so what does that mean? Remember here, Vj is a vessel size. It's a continuous variable greater than or equal to 0. Nj is a number of units. Bi is a batch size. TL is a cycle time of product I. Right? So all these are variables greater than or equal to 0. Let's replace these variables with an exponential of another variable, right? Because the exponential function is always greater than or equal to 0, right? And then this small Vj variable will be unconstrained, right? Since the exponential function always give you something greater than or equal to 0. Okay, so let's just replace them by these variables, small Vj, small nj, lowercase bi, and so forth. Okay. Now, the other tricky thing here is nj is an integer variable, right? Because it's a number of vessels. You have to make sure they satisfy integrality constraint. So here we just did a very simple trick that's represent them using the sum over some k times a binary variable, where let's assume the upper bound of nj is nj overline. The number of units cannot exceed a given number. Here we define some binary variable to say if yjk equals to 1, that means the number of units at state j equals to k. Right? So basically, if you want to replace, let's say if you have a, let's say, integer variable, nj is an integer variable between 0 or and 10, right? It's an integer variable. Then you can replace nj by the sum over, let's say, k from 0 to 10, k times yjk, where yjk is 0, 1, and then sum of yjk equals to 1. Right? It's like you have an integer variable between 0 and 10. This binary variable yjk help you choose what is the integer you are going to select between 0 to 10. Right? So that's a very simple trick to convert an integer variable into the sum over some binary variables. Okay. Yeah, so that's what basically what we did here. And then nj is the log of capital Nj, right? And then similarly, you could take the log of k and represent nj this way. Okay, this is a log transformation. Now let's consider the objective function, right? So the objective function is nj times alpha j times vj raised to the power of beta j. Right? Because of this exponential transformation, multiplication will result in addition once you have this exponential term, right? At the end of the day, you have something exponential of some linear functions, right? Exponential function is a convex function, right? So therefore, you kind of convert the non-convex function into a convex function. Now the objective becomes convex. And similar trick can be done for the constraints. You have this constraint vj greater than or equal to ij times bj. Since both the left-hand side and the right-hand side are greater than or equal to 0, if you take the log on both the left-hand side and the right-hand side, these constraints still hold, right? Because log is a monotone function, right? If left-hand side is greater than the right-hand side, you take the log, it should still hold. So after you take the log, you replace the capital Vj with the smaller Vj, right? So all the lowercase variables are the logarithm of the capital variables. Okay. So this constraint becomes linear once you take the log, right? Then, especially if you take the log of this constraint, it also becomes linear. There's nothing special about that. Remember, this constraint used to be a non-convex constraint, right? You have the ratio of qi and bi. This is a non-convex problem. But after you take the log, the same thing happened, right? You could. Oh yeah, actually you didn't take log. You just replace these b variables by the by this exponential of b, and then you replace TL by the exponential, right? So then you have the exponential function of the log transform variable that is still a convex function. The exponential function is a convex function. So with that, the advantage is you can solve the problem as a convex MNLP. At least the continuous relaxation is convex, right? Solving convex problem is much easier than solving a problem where the relaxation is non-convex. Okay. Yeah, so that's sort of the trick to solve this problem. Again, the major takeaway here is you have a non-convex problem, but then you apply this log transformation trick, and it is converted to a convex problem. For some of the problem, you can do that, but not all the problem. Okay, yeah, yes.
And before you said that sometimes we do a convex approximation.
Yeah.
Is this one not an approximation? Is this one exact?
Yeah, this one is exact, right? Because you just take the log, there is a one-to-one mapping between the log transform variable to the original variable. Yeah. Yeah, so with that, you could formulate this as a convex MNLP. And this basically summarizes all the constraints. As for references, there are different references you could look at. One of them is a textbook by, maybe some of you have interacted with Professor Talamalani from the business school. So basically, his PhD thesis has been turned into a textbook. Right? So that also gives you a sense of how much you can achieve during your PhD. Right? So So what he did during his PhD has turned into a very classical textbook in global optimization. There is also another book by Haas and Tui. It's also a classic reference on global optimization. I use some formulation for the k-means clustering problem from this paper. There are also some references on packing problems. Also here there is a lecture by Shantanu Dey, who is a professor from Georgia Tech. He had a very nice lecture on convexification in global optimization at the IPCO summer school. IPCO is one of the major conferences in integer programming and combinatorial optimization. Right? And the last trick is from my PhD advisor's PhD thesis paper. Right? So in his thesis with Professor Roger Sargent, they came up with this trick to log transform the problem into a convex problem. Okay, so you could check those references if you are curious about one of these topics.